Grade 12s, welcome to our first lesson in our unit number 2, which is electrochemistry. And I think you're going to like this unit actually. Once you figure out the charges and adding and subtracting and balancing things out with regards to electrons, it actually becomes a unit that I find most students understand very quickly and easily. So just be thinking about that. The content we're going to go over in this little learning block you're going to come back to by the end of the lesson today, and then tomorrow again review it. So you're going to review it a little bit, but it may seem a little bit basic to start with, and it will come back to it. You'll be able to understand it as we go a little bit. Okay, one of the best little graphics I've found for this is this adorable little cartoon. This is what we call an electrochemical cell. We're going to look at how you can capture those electrons as they're moving from one substance to another, but there's a lot of information in here. This is one that you might even want to use as a summary diagram. I have a little black and white sketch of this one, so I might post that one. But there's a lot of terminology. Do you see there where the anode is, where the cathode is? These are the terms we use for the substances that lose electrons, while other things are gaining electrons. And so it's this flow of electrons through this cell or battery, if you will, that actually can be captured. And so you can see the light bulb there. And as the electrons flow through, well, that's exactly what's happening. So we'll come back to this diagram here, but even take a look at the terms oxidation, reduction. Have a look at these little ionic equations down in each of those beakers, and you can follow the flow of the electrons. You notice that something's losing electrons and something's gaining electrons. We're going to be accounting for all of those electrons. We're not going to lose any electrons. So just like when we do our balanced chemical equations, where we account for all the same number and type of atoms on both sides. You know how we do that, and you're used to doing that. This is the same kind of idea, except in this concept, we're going to be using electrons. And so we're not going to let any of those electrons get lost. We're going to be counting them. So you can guarantee that the number of electrons lost on one side of an equation is going to be equal to the number of electrons gained on the other side. Okay, so we're going to account for that, and we're going to do some terminology that talks about the difference between them. Okay, so the first thing that I want to show you is that, up until now, you've been talking about the ionic charge. Something has a 2+ charge, so that would be any of the atoms in group number 2. Well, when we're talking about something called the oxidation number, it can be the same thing, but sometimes it can be different. Okay, because in a chemical reaction that's called a redox reaction, one of the elements loses electrons, one of them gains electrons. So you can have different oxidation numbers. And so in this lesson here, I'm going to show you how to figure that out. You'll also notice that we'll use the oxidation number with the charge first and then the number. Okay, so whereas 2+ was an ionic charge or an electric charge, however you use that term, we'll say +2 is the oxidation number. And again, sometimes it's going to be very much the same. The oxidation number could be the same as the ionic charge, but in a chemical reaction where electrons are getting transferred, then it's not going to be the same thing. Okay? All right, so here we go. This is what we call these reactions. We call them a redox reaction, okay? So all chemical reactions can be classified under these two broad categories. They're either no electron transfer or there is an electron transfer. And the ones that are having an electron being moved from one to another are called redox, short form for reduction and oxidation. Okay, what reactions don't involve electron transfer? These are, here we are, found in reactions which involve only the separating or rejoining of ions. Most double displacement reactions don't involve any electron transfer. Okay, so these are ones that you've been used to seeing in grade 10 and grade 11. Here's a simple example. Silver nitrate and sodium chloride react to give me silver chloride and sodium nitrate. If you look at the charges, those ionic charges on each side, nothing's changed. Okay, this is just a plain old double displacement reaction. This is not a redox reaction. You can't, if you separate these half things, you can't actually capture the electrons. Okay, so we're going to be looking at in this unit reactions where there is a transfer of electrons, okay? And we call these redox reactions. Here's how you remember which one's the oxidation and which one's the reduction. You're going to remember this little acronym right here. Leo the lion says GR. Okay, there's a couple of other little acronyms, but that's my favorite one. That's the one we're going to use. Leo the lion says GR. If you lose electrons, that's oxidation. Gaining electrons, that's reduction. Okay, sometimes I say that little acronym in my head all the time if I'm answering a question or explaining. I'm always like Leo, GR. It's one of those things that you want to refer back to this acronym, and then you will be able to do all the questions from now on. Okay. All right, step number 1, you need to assign an oxidation number, okay? Because to figure out if it's a redox reaction, we're going to see if the oxidation number changes for a particular atom if you see it on the reactant side and the product side, okay? So we're going to be comparing those oxidation numbers. So here's how you do that, and this is your first part of unit number 2. So the oxidation number, here's by definition, is the charge that an atom in a substance would have if the electron pairs in the bond belonged solely to the one that was more electronegative. An ionic compound where there's an actual transfer of electrons, the oxidation number is the same as the charge of the ion in the compound. Sodium chloride. Sodium has a 1+ charge. Its oxidation number is +1. In a covalent molecule, because the electrons are shared, remember they're not transferred, the oxidation number on the atom is equal to the hypothetical charge on the atom. Okay, so you determine that by assuming the electrons have been transferred to the one that's more electronegative. How do you know which one's more electronegative? You can use your trend from the periodic table, or you can look on your periodic table and read the number. It'll tell you which one's more electronegative. So you figure that out first. Then you could count up the number of electrons around that atom, and you can give it its oxidation number. Okay, here's an example. Carbon monoxide. Which one's more electronegative? Oxygen. Good. So let's assume that the oxygen will then have that pair of electrons around it. Okay, oxidation number +2. Oxygen is said to be acting as an oxide in that compound. Okay, OF2. Fluorine is more electronegative than oxygen, isn't it? It's the most electronegative one on the periodic table. It would be assigned a negative oxidation number, okay? And so oxygen is said to be not acting like the oxide, and it would have a charge of +2 in that circumstance. So you can see how it's going to be different, okay? We know that oxygen, we know the ionic charge of oxygen. That's not what we're dealing with right now. We're going to look at which one is more electronegative, which one holds that pair of electrons closer to it. That's what's going to be the oxidation number. So when you look at an equation, you can see that some electrons are lost for something, they'll be gained by others, and the amount of loss and gain is going to be balanced. Okay, here are the rules. They're written right here on your sheet, so you can just simply refer back to the rules. The first one you're going to want to remember because you're going to get tricked on the second page. The oxidation number of atoms in a pure element is always going to be 0. That's a 0. Okay? Well, that's a little thick. Okay. Number 2, certain elements have the same oxidation number in all or almost all compounds. And of course, group 1 +1, group 2 +2, -1 +2. Oxygen as an oxide or sulfur as a sulfide, -2. And a polyatomic group of ions, we're just going to keep it grouped together. Of course, it's going to have the charge of that ion. So for example, carbonate, CO3 with a 2- charge, the oxidation number of that carbonate is going to be -2. Okay, fairly easy. Let's see. Exceptions. In metal hydrides, hydrogen has an oxidation number of -1. In a peroxide, oxygen has an oxidation number of -1. Okay, star this because those are the little tricky ones you're going to come back to. Okay, number 3, the sum of all the oxidation numbers in a neutral compound equals 0. However, if the sum of all the oxidation numbers the sum of all oxidation numbers of all the atoms in a polyatomic are obviously going to be equal to the charge of the polyatomic. So that group of atoms has an overall charge. Here are the two examples down below. Okay, if you were to find the oxidation number of the atom that's bolded, so that's what this question is asking us for, you need to figure out what's the oxidation number of manganese. So it's in a particular compound, potassium permanganate. Overall, this compound has a 0 charge, no charge to it. We know that potassium has a 1+ charge. I have one thing with the 1+ charge. Remember doing the zero-sum rule here, same kind of idea. Oxygen in a compound like this is going to have a -2 oxidation number. So manganese, therefore, oxidation number of +7. Okay, this is the show your work stuff that you're going to have to complete. And then once we get to the next page, if you're good at doing your algebra in your head, then you can just simply, put the answer down. Now, this is our chromate polyatomic. Overall, it has a -2 charge. And the question says, I want you to find the oxidation number of chromium. Okay, so here we go, right? I have 7 oxygens. Each oxygen has a -2 oxidation number, so that would be -14. However, it has an overall charge of -2, and I know that I've got 2 chromiums. Chromium is going to have an oxidation number of +6. Now, why are we going to be doing this? We're doing this because we're going to be then looking at the oxidation number of the certain elements in a chemical reaction, and we're going to be looking for which element and which ion, like which one gets oxidized and which one gets reduced. Okay, so we have to see which one goes up and which one goes down by a factor of how many electrons, and then we can actually use that to help us balance chemical equations by using the oxidation number. It's actually quite fun. Okay, so we'll get to that. So step number 1 is simply just figuring out what is the oxidation number of the one that's bolded based on the rules that are on the previous sheet. Okay, so here we go. I'll do one more with you together, and I know there's not a lot of rough work on the page if you happen to print the page. If not, you're just jotting these down on a piece of paper. I did the rough work for all of these as well. Looks like this, a whole sheet of paper. Again, do as much or as little rough work as you need. For the first one then, okay, HASO2. If you wanted to do the rough work for this one, I have one thing with a +1 charge. That's my hydrogen. Okay, I know I have one AS, and that's like I'm solving for that one. That's my X. I know I have 2 oxygens, and every oxygen has a -2. Overall, this compound has no charge to it, so it's going to have to equal to 0. Okay, so that's a +1. +1x, if you will, plus -4 equals 0. AS equals +3. And the oxidation number of my AS is going to be +3. Okay, want to do the next one? Can you do the next one in your head? I bet you can. There's nitrate with a -1 overall charge, so therefore the potassium's oxidation number is going to be +1. Okay, manganese, can you do these? Pause the video, do all of them, and then check the solution set. Okay, once you get down to the bottom, the next part is to look at half reactions. Okay? Okay, you've paused the video, you've done all of your oxidation numbers, you feel good about that? All right. Here's what we learn about taking our oxidation reduction equations. Because they're coupled together, okay, we can separate them and we can show that one will be oxidized and one will be reduced. By how many electrons? That's what we're going to be putting down in our what we call half reactions. Okay, so they're coupled. A redox reaction can be analyzed by studying the other oxidation reduction reactions separately, and the separate parts of the redox reaction are what we call half reactions. So does that make sense that half of the reaction is going to be an oxidation? The other half is going to be a reduction, because overall we're going to make sure that we have lost and gained the same number of electrons, and that's going to give us our overall reaction. Okay, here's a typical redox reaction to get us started. 2Mg plus O2 gives me 2MgO. Okay, now you can even have a look at this equation here and you can do the oxidation numbers, and I bet you can see which oxidation number has changed for which atom. Okay, see if you can do that in your head. During the typical formation of this ionic substance, oxygen molecules collide with magnesium. Each magnesium atom loses 2 electrons to become magnesium 2 plus. Each oxygen atom gains 2 electrons to become O2 negative. The oppositely charged ions then attract to form MgO. Okay? The oxidation of magnesium and the reduction of oxygen, we're going to show that as the 2 half reactions. So how do I know that? Well, I know that one is oxidized and one is reduced. So when I show that as my half reaction, I know that magnesium goes from an oxidation number of 0, right? Because that's what all elements would be. This Mg2 plus has an oxidation number of plus 2. Therefore, it's lost electrons. Okay, follow my wording here. A loss of electrons, that's oxidation. Remember Leo the lion? Losing electrons is oxidation. And so when something loses electrons, where do those electrons show up? If they've lost electrons, the electrons are going to show up on the product side. Okay, so you would write the half reaction as Mg to Mg2 plus 2 electrons. Let's do the reduction half reaction. I know that I have oxygen, which is an oxidation number of 0, right? And then I have O2 minus. The oxidation number has gone down, okay? It's actually gone reduced. It gains electrons. It's called reduction. And where do you show the electrons? You show them on the reactant side because they've gained electrons. So something that gains electrons is going to be on the reactant side because it's gained electrons. Okay, do you see that wording there? Think about that. All right, and then you can see this. Because I had 2 magnesium in my original equation, here, let me make that bigger, okay? Here's where I have to account for that 2 magnesium down below. 2 magnesium gives me to 2 Mg2 plus 4 electrons. Can you see where we've got 4 electrons in total lost? Because every 1 magnesium loses 2 electrons. 2 magnesium, I've got to account for the 4 electrons in total. I'm going to take my reduction half reaction and I have to show that as the total number of electrons gained is 4 electrons. The 2 half reactions can then show the overall reaction, and I want you to see this, okay? Oh, sorry, let me just do it this way, okay? Our electrons on the product side cancel out my electrons on the reactant side, and there is my final chemical equation. This again is the one that I started with. All I did was figured out which one was lost and gained. I separated the 2 half reactions where one's oxidation and one's reduction, added them up, accounted for my balancing of my electrons, and then you can see overall no charge because my electrons have been lost and gained the same on each side. Okay. Again, what's that called? That's called balancing half reactions, okay? Let's look at this one. Now, I always usually write this little summary every time I go to start this, these types of questions. I want to remember Leo Ger. I want to remember that losing electrons is oxidation. And so if you're losing electrons from the reactant side to the product side, losing electrons means your electrons are going to be on the product side because you've lost them. And you see an oxidation number change going from a lower value to a higher value. So when something experiences oxidation, the oxidation number will go up. The electrons will be on the product side, and that is because it's a loss of electrons. Conversely, Ger, gaining electrons is reduction. The oxidation number will go down. The electrons will be on the reactant side because they are gaining electrons, okay? Try to get that little summary somewhere on a nice summary sheet so that you can go back to it, talk your way through it to see if you can, then it'll become a lot easier if you understand that, Okay? All right, here's an example. If you've got manganese, yeah, yellow's good. Okay, 7 plus going down to 4 plus. So somewhere along the line, I had this in a balanced chemical equation. I checked the oxidation number of the manganese on the reactant side, and where I found it on the product side, it went from a 7 plus down to a 4 plus. So what does that tell me? That tells me that the oxidation number went down, that it's a gain of electrons, so that I have to put the electrons on the reactant side by how many? Well, how do I balance out the charges? 7 plus 3 electrons will give me a 4 plus. That's how I know how many electrons it actually gained. Okay, is that easy? Yeah, okay, I think it probably is. So then what you want to do is you want to balance these. These are just partial half reactions, and I want you to see if you can figure it out, okay? Cu2 plus going to Cu plus. What's happening to the oxidation number? It's going down, okay? When the oxidation number goes down, that means it's a reduction. That means you put the electrons on the reactant side because they've gotten reduced. How many electrons? Well, you have a 2 plus charge and a 1 plus charge. Clearly, you're going to be adding 1 electron to the reactant side. Okay, chromium, 6 plus to 2 plus. 6 plus to 2 plus. It's a reduction because my oxidation number goes down by a factor of how many electrons? 4. Okay, it's a gain of electrons, it's a reduction. My electrons will show up on the reactant side, and that's my balanced half reaction. Okay, call it a reduction. I'm going to pause right now, or you pause, and I want you to fill in the rest of this. Okay, once you get that done, then I'm just going to move on where you're going to look at now 2 parts. You're going to look at the half reactions that we have, and you're going to be filling in for this equation right here. What I want you to think about when you're doing the last 3 on the bottom page, the bottom of the page here, I want you to remember that when you're dealing with an ionic compound, okay, metals will be getting oxidized. The ions will get reduced. So you want to think about this in terms of like, what if I had a stick of silver and I put that silver into a solution that had some chloride ions? How do you know which one's going to get oxidized or which one's going to get reduced? Well, always remember and come back to the idea that the metals will get oxidized, meaning that it's going to go from a solid metal with a 0 oxidation number to a metal ion because the oxidation number will go up, right? And so silver is always going to look like this, right? It's going to be Ag going to Ag plus because metals will get oxidized, whereas the non-metals are the ones that are going to get reduced. And so you can see chlorine is going to go from a chlorine like a solid form, adding the electrons, and it's going to go to an ion. Okay, so think about that and use that general knowledge to help you figure this one out too. Okay, here's my equations. So I've got these 2 half reactions, and you're asked to figure out the net reaction and then the simplified net reaction. Okay, do you want to do this one together? I could do this one together, or I'll do this one with you, and then I'll let you do the other 2 that are at the bottom. Okay, so if I have lithium and oxygen, I'm going to look at the oxidation number of the lithium on the left-hand side. Is that an oxidation or reduction? And then my oxygen, is it an oxidation or reduction? Can you tell me that first? Okay, we know the lithium is getting oxidized. Why? Because it's going from an oxidation number of 0 to an oxidation number of +1. Increase in oxidation number, that's oxidation. Okay, and if it's an oxidation, where do I have my electrons? Leo, losing electrons. Losing electrons will show up on the product side, and so it's going to show like this. 4 lithium going to 4 Li plus 4 electrons. All right, now let's look at my oxygen. And I know that this is the one that gets reduced because it goes from a 0 oxidation number down to -2. You notice how I always think of that integer scale as a thermometer? I don't know if you've ever done that before where you're like, is it going up or is it going down? I like take my integer scale and flip it like a thermometer. So a 0 is here, negative is here, plus is here, and that just helps me to visualize. It's actually helped quite a few students if you've never done that before, but you guys are all pretty good with your math, so I'm not worried about you learning any tricks like that. You already know that. Okay, O2. How many electrons? I have 4 electrons. Okay, going to 2, that's an arrow. I'm using my Apple Pen for the first time. All right, 2, 2, O with a 2 negative charge. My net reaction, I'm simply going to add them all up, and then I'm going to cancel out my electrons for my simplified net reaction. Okay, so here we go. 4Li plus O2 plus 4E. I'm just adding everything that was on my reactant side for my net reaction. Okay, and that's going to go to 4Li plus 2 O2 plus 4 electrons, cancel out my electrons on the reactant and product side, and my simplified net reaction is 4Li plus O2 going to 4Li plus 2O with a 2 negative charge. Okay, you're going to do the same for the next 2 by looking at them to see which one's oxidation and which one's reduction, and I'll just cover them up so you do that one on your own. All right, and that's it. So draw maybe your integer scale where you're looking at oxidation reduction, draw your little summary like that, or think about your summary like this, and then I'm going to get you to do a little reading in the textbook and check your answers for these ones. Okay, good luck.